everybody! How are you? Welcome for our second and last day of our structured approach to vehicle dynamics simulation. I would like to know what was your feedback for our presentation yesterday? What was the thing that most impressed you? The biggest insight that you have from yesterday? I would like to know if you guys can put it in the chat. Would love to follow up and see how we could help you and maybe to dive deeper in these topics today. Did you guys think were useful? Did you learn something? We exceed your expectations? What do you think? Today we're going to speak about the skid pad optimization and a four-wheel transient model for load transfer. And we would also like to know your expectations for today, what you expect to learn. We'll start in a few minutes, a few seconds. So please tell us your opinion, what you thought about it. If you invite a friend to watch the live with you. Okay, Antonio said that he would like to see more about modeling of the systems. He said that was very interesting yesterday. Thank you very much. Yeah, it was lovely. Thank you. Thank you very much, guys. We are happy that we are being useful for your professional path, and we're happy to be useful for you. So before we start to dive into the content, we would like to pass the word to our president, Claude, to say a few words like yesterday so we can start.
Hello, everybody. Welcome back to the second day of this webinar about simulation, and as we're going to speak about optimization. Just one word to clutch with the question that Danielle received about modeling. Be aware that OptimumG is offering two kinds of seminar for the public. One is applied vehicle dynamic, the other one is data-driven. You can have the details of the content of this seminar on our website, OptimumG.com. And we also have seminar that we give in-house that one obviously are not on our calendar, which is published in different companies, automotive, and also parts like damper brakes, ABS, and so on. Seminar that we give, and the content is defined depending the needs of the company. All right, let's go to our topic here. When it's about simulation, a lot of people are using multi-body dynamic software. They are pretty good on the software, but at OptimumG, we have a different approach, which is the abstract approach. I have to tell you that I've been pushing this way of working inside OptimumG for the simple reason that I've been very impressed by the teaching 50 years ago that I received from one of the teachers in mechanical engineering who spoke to us a lot about Darwin and the theory of the evolution. At the beginning, I was listening destructively to the teacher, but I got more and more interested interested when I understood that the essential thing that form are defined by the function and not the other way around. When you have a multi-body dynamic software, you start with the form and you do some virtual ISO test, lap time simulation software, whatever, and you get the result. That's one approach. The other solution is to have an abstract approach. So let me explain in a very few words what you're going to have Luca and Philippe explaining with a skid pad optimization. We're going to make different radius of different skid pads, and we will want to know what's the ideal ride height, or what's the ideal camber, what's the ideal lateral force, load transfer distribution. We don't know what the pickup points are. We don't even want to know where the picker points are, but we will define the different cambers. And as you go from a small to a longer radius, well, guess what? You have more and more roll angle because you have more and more lateral G, especially if it's a race car with downforce. But at the same time, you have less and less steering. And at the same time, also, you have more heave, exactly, especially you have downforce. And from there, we decide ideal camber and also ideal slip angle and vertical load and so on that we want versus the heave, the control, the roll, and the steering. And then we use OptimumKinematics optimization to find what the ideal picker point should be. So we always start with the function and not with the form. That's a nice way to do it. And why? And I'm going to let Felipe and Lucas speak very quickly, but why do we start with skid pad optimization? In racing, there are two ways of looking things. Lap time simulation software will show you that it is always at the apex of the slowest corner, especially, that you make the lap time. If you look for the pure vehicle dynamic perspective, if you have a good speed at the apex, you already have it's going to be easier to have a good car in transient. But don't try to make a transient dampers and so on to patch a bad steady state simulation. So we always start with the skid pad optimization. Then after, the second part that we are not going to speak about is transient at the entry of the corner, where the driver with the notion of stability and control are very much involved. Okay, so skid pad optimization, that's what we're going to speak about here. And Felipe, I think I'll let you speak now. Enjoy.
Very well. So hello, everyone. Welcome back to our second day of our webinar. My name is Felipe Dikir. I am an OptimumG engineer. And today I will be presenting to you one of the softwares that we have developed over a little while ago. And it is the skid pad optimization software and the methodology that we use behind it. So I'm actually going to start just by going over the software that we're going to look today. Just a very quick glimpse of the interface. This software, it is something that we have it as an internal tool. It's not commercially available, though we do want to have a commercial version of it at some point in the future. And we also want to add more optimization features to our software as well. This is a software that we have used in some consulting projects before. And it's a software that took quite an amount of work to do. Claude and I and the other OptimumG engineers, we spent a lot of time discussing what is the best way to do it, sharing different literature recommendations between ourselves to try to learn what we needed to get to it, making some design decisions like when we should invest time in performing some stuff versus another and so on. So it really is a group project. And this is the culmination of it, which is something that we will be discussing further today. So the first tab that I'm going to show you, just a very quick glimpse of what the software interface looks like. This is where we are going to set up the base car that we're going to be optimized. So we have some of our vehicle inputs here, like the mass, the wheelbase, the track widths. We have an aerodynamic map, which is imported from an Excel spreadsheet. We have a tire model, which is imported from a .tir file and so on. We will go into more detail in each of these submodules, if you will. And these base characteristics of the car, these are something that are locked in. This is something that the optimization algorithm is not going to touch. It's the starting point of the entire optimization algorithm. Then the second tab that we are going to look into is the boundaries of our optimization. So the goal of the software is to get an existing car and modify its kinematic characteristics to try to be as fast as possible over skid pads of several different radii. So the way that we do that is that we are defining each kinematic aspect of the car as a given curve. And here is where we are going to define the boundary regions within which the optimization algorithm can work, and also some solver configurations as well. Then over the next step, this is where we're going to define our optimization, the settings for the optimization algorithm itself, which I'm going to explain in more detail as well, and also the different corner radius that the car is going to go through. And finally, the results tab, which is where we can see the results of our optimization in several different ways. We're going to be focusing on our scatter plots here mainly today, but there's also a parallel plot, which we saw a little bit yesterday with the two-wheel transient model that Luca showed. And also some other genetic algorithm specific plots as well. We will be going over the main results later. Okay, so I will be going a little bit back and forth between the software interface and a PowerPoint presentation just to help get some points across. So starting to the presentation today, I wanted to just make a quick recap of what we saw yesterday. If you guys weren't there or if you need a refresher. So yesterday we started by discussing what is a simulation, which is a virtual representation of a real-world system, and how useful it can be in increasing our understanding of the car, be able to predict certain phenomena. And in the vehicle dynamics case specifically, we use simulation to make some decisions in order to have what we would call a better car according to given criteria. Some of the benefits of simulation, which is risk-free experimentation, cost reduction, enhancing our vehicle, the understanding that we have of our vehicle, and probably the main aspect that we're going to be focusing on today, the optimization of the vehicle's performance. Here, a few pros and cons between commercial software and self-developed software. In commercial software, you already have some tools readily available. You don't need to work as much, and you have proof that they work. However, they are limited and they cost more. While if you have self-developed software, you can really tailor it to your needs and you don't need to worry about licensing, but you're going to have to put the work in for it. And the main aspect that we focus on self-developed software, which is why we give it so much value, is the fact that you really need to understand exactly what you're doing. You have control over every single line of code that is executed. And that is what we think that really teaches you about your vehicle's behavior and how you can improve it in some way. Then we talked a little bit about the methodology of going from a simple model to then a complicated model. So you're probably going to start with a very simple model with maybe a mass point in steady state, a fewer number of variables, a fewer number of degrees of freedom, and so on. And then as you get more experience, as your team needs grow bigger, you can invest some time in improving your model, going to quasi-steady state, going to transient simulation, increasing the number of variables that you're dealing with, increasing the number of phenomena that you're able to consider. And then we get to our resume, let's call it that, a summary of the different vehicle models that we have available. And today, the two software that we're going to focus on is first the steady state four-wheel model, which is the skid pad optimization that I'm about to show you guys. And then we will go to a four-wheel transient simulation example, which is what Pedro will show you in the form of a lateral load transfer simulation. Okay, so going over a little bit into optimization again. In general, optimization is the process of finding the minimum value for a given mathematical function, and more importantly, finding the combination of inputs that reach that minimum value. In our case, in vehicle dynamics, what we mean by optimization is that we want to find the combination of car characteristics that can get that car towards a certain goal. In our case, in racing mainly, the main thing that we're worried about, of course, is minimizing lap time, but that can be not the only objective that we have. So in other words, the questions that we are asking is, what is the camber angles, the bump steer, the motion ratios, the Ackermann percentage, and the suspension pickup points that will steer my car towards having maximum acceleration, a higher top speed, an ideal balance, a best ride comfort, and a combination of these. So hopefully this methodology that we present to you today can give you some insight into how we at OptimumG are able to answer some of these questions. And as Claude mentioned, the approach that we have here is what we call the OptimumG's abstract approach. And if you had to define it in a single sentence, we would call it function then form. So it's pretty much divided into two different steps, two different main sections that we go through. The first thing that we're interested in is finding what makes a better car. So which camber gain do I need to make the car go faster? Which bump steer variation, which suspension stiffness, which dynamic ride heights, and many other different variables. And then, and only then, are we interested in how we are going to do it. So which are the pickup points that are actually going to give me the camber gain that I need, the bump steer that I need, which actuator arrangement do I need to have? Am I going to use a torsion bar? Am I going to use an anti-roll bar? Does it make a difference if I go soft spring stiff anti-roll bar or stiff spring soft anti-roll bar? Which static camber and toe values am I going to use, and so on. So these relate to the form, these relate to the how we are going to get to that point. And at first, it's not something that we are worried about. At first, we are only worried about knowing what is our objective in the vehicle dynamic sense. So going into a little bit more detail about how we're going to talk today. So the first part, which is the function, which is finding out what makes a car better. This is the purpose of the skid pad optimization software that I'm going to show you. And pretty much what it is, it's a custom-made genetic algorithm that its full objective is finding out what is the ideal kinematic curves that will result in a faster car going over several different skid pads. So these are only steady state cornering maneuvers. Transient phenomena are not being considered here. Just to give you a quick example of some of the results that we can get. So these graphs are comparing a baseline suspension, so before optimization, and the optimized product in blue and red respectively. And we can see that with the optimization process, we gain about 2.1% in lap time reduction when we compute what would be the quote unquote lap time when you take over each of the skid pads. And you have a clear speed and lateral acceleration advantage as well. And we're going to see some of the reasons why that happens. And then the second part that we're going to tackle is how we are going to do it, going over from the function to the form. And for this, we are going to be using OptimumKinematics optimization module. This is a commercially available tool. I guess some of you are already familiar with it. And pretty much is what we're going to do is that now that we know what is the ideal camber gain, the ideal bump steer, the ideal Ackermann percentage that we need, these kinematics characteristics are going to become inputs to OptimumKinematics optimization module. And that software is going to give us back the pickup points that most closely meet the target behavior that we know will make the best possible car. And an example result that we're going to see later is that the suspension pickup points are being modified here by the algorithm, as you can see on the left, and that it's being modified with the purpose of getting the kinematics behavior of our car closer to what was the objective that we got from the skid pad optimization procedure. All right, so now I'm going to go back into the software interface so we can talk about it in a little bit more detail. The software starts with our design tab. So this is where we are going to put in the inputs for our baseline car. Some of them are, for example, the total mass, the unsprung mass per wheel, the track width, the CG height, and so on. And everything that is inside of this tab, these are things that we assume that at that point in the design process, these are locked. They cannot be changed for whatever reason, either because you already have a pretty good estimate of the weight distribution of the car, for example, or you cannot change the track width because of the rule set or whatever. So all of the different candidate cars that the optimization algorithm will find, they will share exactly the same characteristics. These are not the target outputs of our optimization here. We also have an aerodynamic model So all of the different cars will be using exactly the same aerodynamic model. And as I mentioned earlier, this aerodynamic model is imported from an Excel spreadsheet and then interpolated into the software. So each of these red points here is the downforce coefficient that's coming directly from your aerodynamic map. Either you measured it directly in a wind tunnel, or you have it as an output of your CFD simulation. And then what the software is doing is that it is interpolating these points into this little plane that we have here. And we can see what the interpolation looks like in terms of the downforce coefficient of the car, in terms of the drag coefficient as well. Also the downforce distribution for all of the different ride height combinations that we have available to us. And also another visualization tool that we have here is this correlation plot. So this is pretty much an indicative of the quality of your interpolation function. So the x-axis of each of these graphs is the measured aerodynamic property, what is coming directly from your aerodynamics map source. And the corresponding y-axis is what the software is calculating from the interpolation. And if these two values are exactly equal to one another, that means the point will fall exactly on this line, and we will have a perfect interpolation. So pretty much this is a visualization of the R squared of that interpolation. And you can see that all of the different aerodynamics properties here have a fairly high R squared. Maybe it can be improved with a different interpolation process or adding more data into our data source. But this is good enough for our simulation purpose here. So another input that we have available to us, another visualization tool that we have available to us, is regarding our tire models. Just like the software that we presented yesterday, these tire models, they come from .tir files that you can create with Optimum Tire, for example. And these models, in this case, they are Magic Formula 6.1.2 models, but we can also work with other different tire models like the Passaic 2002, Magic Formula 5.2, and some other options as well. And here, including we have included the visualization option that you can kind of experiment a little bit with how your tire would behave for different input conditions. So, for example, if I change the vertical load, or if I change the inclination angle, how much does that change my lateral force, my self-alignment, some other variables as well. And we also have it for the rear tire as well. Sticking to tires, some other visualization tools that we have. So this is a 3D map that we have of the different slip angle combinations with inclination angle combination and the resulting lateral force at a given vertical load that we can change here. And also the same for a self-aligning moment. So we can have an idea of how much is the maximum lateral force that tire can provide us at that vertical load, and which slip angle and inclination angle combination will result in that peak lateral force, and also self-aligning moment as well. And also sticking to tires, again, tires are the most important component that we have on the car. And even before performing any sort of simulation, there is already a lot of information that you can extract only from having your tire models, which is something that most Formula student teams, for example, have available to them. You need to know how to extract use of your tire models. This is also another very, very insightful graph, which is the slip angle, which generates the peak lateral force versus different vertical loads. And here, one thing that we can very clearly see is that we will need a higher amount of slip or negative slip angle for a less loaded tire, which means that probably our inside tire will have more slip angle than the outside tire. And this could point us into a given direction for example, our steering system design. We will see how the optimization algorithm fares with this claim. If it agrees with us, if it proves us wrong for some reason, we will see how it does. And then the final input that I wanted to show you relates to a powertrain input. So we will input a speed versus torque characteristic here. In this example, this is an electric car, so that's why the curve looks in a little bit of a specific way, and it only has a single gear ratio as well. But if you want to change this value, for example, the plot will update in real time as well, and you can run the simulation with the new values that you have. You can also see, for example, the torque that goes to the differential versus the different vehicle speeds. And if you add more gear ratios here, you can see, for example, the effect that each of them will have, for example. Okay, so this is some of the vehicle inputs that we have available here. Again, all of these will not be changed throughout our optimization process. This is a starting point that we are feeding into the algorithm. Then after that, we are going to go into the setup portion of the software. This is where we are going to set the boundary regions for our optimization algorithm. So what the algorithm is targeting to modify to get to a better result is the kinematic characteristics of the car. So the specific characteristics that we are going to optimize are the heave frequency versus the ride height, the toe variation versus the suspension travel, in other words, the bump steer, the camber variation versus suspension travel, camber variation versus steering angle for the front axle. We also have the steer ratio versus the steering wheel angle, the Ackermann percentage, and the lateral load transfer distribution versus lateral acceleration. So all of these kinematics parameters, we have them be correlated to one another by some function. And what we are doing here is setting the limits that these functions can be in our solution space. So to help explain to you a little bit better, I go back to the PowerPoint. So for example, here we have the heave stiffness of the car, which will vary with the ride height. Again, we're not interested at this point how we're going to do it, if we're going to use nonlinear springs, if we're going to use variable motion ratio, and so on. We just care about what should be the resulting stiffness at each of the different ride heights. And these two curves that we have here, the red and the blue curve, these are the limit regions that the optimization algorithm is allowed to search within. So one of the different possibilities that the algorithm will find will be, for example, this green curve, another possibility, this yellow curve, and another possibility, this little pink curve here. So all of the different cars that the optimization algorithm is going to test are going to have the stiffness versus ride height behavior sit between the red and the blue curves. So this is how we're going to restrain the optimization algorithm to find some results that will actually make sense to our car. And we can change these characteristics here. So for example, if I change this coefficient, the curves will move around, and we will have a different solution space that the software is going to look for. Let me just get this back here. Yep. Okay. So now that we have set the boundaries for our optimization purpose, we will go into the settings, the configurations of the optimization algorithm itself. And to explain that, I, again, will switch back to the PowerPoint slide, just to make the point a little bit more clear. So the way that this works is with a generic algorithm, and pretty much the way that the generic algorithm works is that it's going to create a set of different vehicle possibilities, each of them having their own kinematics characteristics, and then it's going to select the fastest vehicle. So it's going to figure out what are the characteristics of the fastest cars, and it's going to create more cars closer to those characteristics, so favoring those characteristics, pretty much as you will have in a natural selection process, which is where the genetic algorithm got its name from. And the way that it's going to do that is with 3 different procedures. So the first one is what we call elitism. So it's pretty much, we have one individual in the current generation N, and we want to create the individuals that will form the next generation of cars. And what elitism is going to do is that it's going to simply get a car that already exists. It's going to create a perfect clone of it, no modifications made whatsoever, and it's going to add it to the population of the next generation. So this is just something that the algorithm does to preserve the best results that it already has found. The second way that we can create more cars as the algorithm progresses is by a process called crossover. So pretty much what we're going to do is get two existing cars. We're going to combine characteristics of them in some form, and that will result in a new car on the next generation. And then the final way that we can create a new car from an existing one is by the mutation process, which is by having an existing car and you add a small random variation to its characteristics, and there you will have a new car on the next generation. And the proportion of individuals that are created from each of these different procedures is something that you can tune in our software interface. So these are the options that you can have here. So for example, I can control how many individuals will be cloned from the elitism procedure. We can control some bias percentages for the crossover and mutation procedures as well. And these will control how strong or how weak each of these functions are compared to one another. And then another thing that we are going to set in this tab of the software in our optimization settings is to define the different turn radii that each of our cars is going to be running through. So in this case, the results we are going to analyze is for different cars going for 9 different skid pad radius between 45 meters and 165 meters. Here also we could select more objectives. So instead of only having a fast car, we could also try to make it drivable by changing the control and stability targets, which are some driver-specific metrics. Each driver will tell you that a different amount of control and stability for each corner will be ideal. So because we don't have a driver at this point, we are not going to be touching these targets for now. So the weight attributed to them is equal to 0. We are only going to try to make the car go faster without really caring at this point if the drivers that we have to drive it will actually be able to do so. So this is pretty much how you're going to set up the entire optimization software that we have here. And then after that, we can run the simulation, and I'm going to go back to our slide here to show you some of the main results and conclusions that we can get from the optimization algorithm. So the first thing that we're going to see is this little plot here. So the y-axis on each of these graphs is the average speed when we take the average of the speeds that each car goes over the 9 different skid pads. And the x-axis of each of these is pretty much the boundary of for each kinematic characteristics of the car. So for example, the coefficient that is going to control the front stiffness versus heave kinematic curve, which is something that the algorithm is going to be changing, the values of these coefficients can sit between 0 and 0.25, for example. And the red points are the individuals, the different cars that are present in the first generation, and the yellow points are the cars that are present in the last generation, which is the 100th generation in this case. And the idea behind this plot is to try to understand some aspects of the optimization procedure itself, of the quality of the optimization process. And we can very clearly see that initially our population is very diverse. So we don't have any particular trend in any of the different kinematics aspects that we are aiming to optimize here. But we can see that as the generations go on, we can see that some of these kinematics parameters, they have clear favorites, and they are converging somewhere, and especially the ones that are more closely converged. So for example, the lateral load transfer distribution or the roll gradient, for example, on which we can see that the last generation has pretty much very similar characteristics. This is an indicative to us that these parameters may be more closely related to the resulting speed of the car. The next results that we're going to to see are related to the what we're calling the lap time, which is the amount of time that it would take for our cars to go through 360 degrees of the skid pad. Of course, in a real track, your car will not take 360 degrees in the same corner, but the percentage of improvement will be the same, whether you're only talking about the apex performance or you're talking about a full 360 degrees. And we can very clearly see, as I showed you before, that the optimized car is markedly faster. It has a consistent speed advantage, has a consistent lateral acceleration advantage compared to the non-optimized car. We have pretty much 0.1 G here at every single corner. And we can see that the lap times are also diminished. And when we plot that in a bar plot here, we can more clearly see that we can have, on average, 0.3 faster per corner radius, which means a performance improvement of about 2.1%, which in racing, 2.1% can make a very large difference when you're talking about thousandths of a second between first and second place. All right, so the next results that we're going to talk about, I brought some of the variables that we can calculate from the optimization procedure. Each of these relates to a different subsystem of the car, and we're going to see how the best car that the optimization algorithm found behaves in these metrics. So the first thing that we're going to see here is the different slip angles that we have on each of the 4 tires. And going back to the slip angle that generates the peak lateral force versus vertical load graph that I showed you earlier, we can see that on the front axle, the inside tire, which is the left tire, all of the corners that we are taking here are to the left. So the front left tire, which is the inside one, has a greater slip angle value, has a more negative slip angle value. And this is something that we imagined we would see from the characteristics of the tire model that we saw earlier. And indeed, the optimization algorithm is agreeing with us that having more slip angle on the front left than compared to the front right will help us get to a faster car. On the rear axle, on the other hand, the slip angles are more closer to each other, but we don't see exactly this difference, and this is a consequence of the toe-in variation that we have on the outside tire. Showing some more results related to tires. So the next thing that we can check is the instant cornering stiffness. So for those of you who need a refresher, the instant cornering stiffness is defined as the gain of lateral force per degree of added slip angle. If you have a cornering stiffness equal to 0, that means that you have the maximum lateral force that tire can actually provide to you on that vertical load, on that camber, and on that pressure. If you have a cornering stiffness greater than 0, that means that you have a slip angle which is greater than the one that provides maximum lateral force, which means that your tire is being slightly overutilized. And pretty much the way that we get to our cornering stiffness is that if you plot lateral force versus slip angle curve, pretty standard stuff from your tire model, and you take the derivative of it, you will get to our cornering stiffness. So you can see that the cornering stiffness has its maximum absolute value at 0 slip angle, which is where the lateral force curve has its largest inclination, and that when your slip angle is at the peak, which is at about maybe 5.4 degrees maybe, that's when you have your cornering stiffness be equal to 0. And when we see the cornering stiffness results for our skid pad optimization here, which are the y-axis that are on the left side of each of the graphs, we can see that the cornering stiffness of all of the 4 tires are relatively small, which means that our optimization algorithm is able to put the tires fairly close to their force generation limit. We will see this in a more clearer way in the next slide as well. And we can also see that on some of the turn radii on the outside tires, so for example, the front right tire in a turn radius of 135 meters here, for example, it has a positive cornering stiffness, which means that we have a slip angle on that tire, which is slightly greater than optimal. And we will see that again with the tire usage metric that we have here. So we spoke a little bit about this yesterday. Tire usage is a very simple metric to calculate, and we will show you how to do it. And pretty much what it is that it's an attempt to quantify how much or how efficiently a tire is being utilized in terms of its force generation capacity. And you can do that either in the lateral sense, in the longitudinal sense, or also in combined loading conditions. And we can calculate that in two different ways. We can have that in a force usage sense. And in that sense, it is defined as the force that your tire is actually generating at that point in time, divided by the maximum force that it could possibly be giving you. Or you can define that in terms of slip, which is the current slip angle or slip ratio that you have in your tire, divided by the slip angle or slip ratio, which will generate the maximum force available. And the peak performance of your car will necessarily always, all of the time, be achieved when at least one of your tires is at 100% usage. So the way that we compute this is that, for example, we have here our force versus slip curve. This can be either lateral force versus slip angle or longitudinal force versus slip ratio. And we can see here that this is our point P here. It's the point where we have the peak force. And correspondingly, we have the slip angle or slip ratio, which generates that peak force. And if we have, for example, our operating point number 1 here, it will generate some amount of force at some amount of slip. And the way that we're going to define the force and slip usages is by getting that value of force and dividing by the peak force times 100%, and getting that amount of slip and dividing by the slip angle or slip ratio, which generates that peak force, times 100%. And again, if we have another operating point here, for example, we will calculate it exactly the same way. We take our force value number two and divide it by the peak force, and our slip value number 2 and divide it by the slip that generates that peak force. And we can see here that in the case of our second point, we will have a slip usage which is greater than 100% because we are already past our peak slip angle or peak slip ratio. And when we go back to our optimization results, here on the left side, we have the slip angle usage together with the slip angle of each tire. And on the right side, we have the lateral force usage also together with the lateral force that is being generated by each of the 4 tires at each of the different skid pad radii. And we can very clearly see on the right side here that all of the tires have a very good usage to them. All of them are consistently above 90%, and especially the outside tires, which are the more heavily loaded ones, they stay pretty close to 100% for all of the different turn radii. And that pretty much means that our optimization procedure is doing a good job in trying to extract every bit of performance that we have available to us. And on the left side, for the slip angle usage, we can see that on some of these corners, we have a slip angle usage which is greater than 100%. And these mean that we are past the peak slip angle of that tire on that corner. And these points will correspond to the positive cornering stiffness that we saw earlier as well. So going over to another subsystem, if you will, of the car, another aspect of the car. Here we're going to talk a little bit about the ride heights and aerodynamics that we have on the car. So as we know, the aerodynamics devices that we have on the car are extremely sensitive to front and rear ride height. Also some other variables which not everybody considers, including yaw angle, roll angle, and steer angle of the front tires, for example. But the main ones are the front and rear ride heights. And for that reason, it's very important on an aerodynamic car that we can control the dynamic ride heights that we will have at each of the different corners. And we do that by having a heave stiffness, which is usually variable and which usually increases as the car goes down. So this is intentional. This is something that you will see in pretty much every race car that you have. And the main reason that we have it is to help avoid the car bottoming out in high-speed corners where you have maximum amounts of downforce, which is further compressing your spring and getting your chassis closer to the ground, but also to help control the ride height and ride attitude of your car to keep your aerodynamic devices working at an optimal operational window. So these are the dynamic ride heights and the corresponding stiffnesses that we have at those ride heights that our optimization algorithm is finding to be the best. We can see that the rear axle has a little bit more movement because it is a softer suspension to begin with, and also because it does have a greater amount of downforce, which I'm not showing here, but that's also another reason why it compresses a bit further. And we can also conclude here that even though the rear axle has a bigger motion than the front, both axles still compress relatively little, which basically what this can suggest to us is that this car specifically does not have enough downforce on that aerodynamic map to compress a suspension this stiff. So you could probably have a softer suspension if that would help you, or you could run maybe a lower ride height, or you could try to focus your attention into improving your aerodynamic package and get a more suitable downforce for a car of that type, for example. Then continue on the aspects of the stiffness of the car. Here we're going to talk about a little bit of roll and lateral load transfer. So as we saw earlier, one of the things that is being optimized on the car is the lateral load transfer distribution that we have available. And this is the behavior that the algorithm found to be the fastest. So what is happening here is that we have a variable lateral load transfer distribution. As the speed of the car increases, we will have a lateral load transfer distribution, which will get progressively further towards the front. And so with more load transfer happening on the front, that means that we will have a behavior that tends to high-speed understeer. This is usually what we see with in racing cars, because having high-speed understeer is a lot easier to drive than having high-speed oversteer. So usually this is the preferred behavior of the majority of the drivers. Of course, there is a possibility that you can have excessive high-speed understeer, but this is just a general trend that you see. And the way that we achieve this variable lateral load transfer distribution is that we will increase also the roll stiffness distribution of the car. So as we know, the stiffer axle will tend to have a greater lateral load transfer distribution. So in our case here, the roll stiffness of the front axle is increasing more than the roll stiffness of the rear axle. And that's why the lateral load transfer distribution is being further and further biased towards the front axle. Going quickly over to our steering system. Here we have the different steer ratio values at each angle for the steering wheel, and also the Ackermann percentage that we have. We can see that for all of the different turn radii that we have an Ackermann percentage which is greater than 100%. Here we are defining Ackermann percentage as the inside steer angle divided by the outside steer angle. So having an Ackermann percentage which is greater than 100% essentially means that the inside tire is steering more than the outside tire. In other words, we have a pro-Ackermann geometry. And this is one of the reasons why we saw earlier that the inside front tire will have a greater slip angle value than the outside tire on the front axle. Also, the steer ratio of the car is also varying in this example, though it doesn't vary too much, but it's also something that we can modify depending on the way that our suspension and steering kinematics is built on the car. So these are just some of the main results that I wanted to bring to you. There are many more outputs that the software can calculate, and this is the complete list. So it relates to several different categories or subsystems. We have outputs related to lateral acceleration, yaw moment, heave frequencies, drive torques on each of the different wheels, the throttle position. We have some aerodynamic parameters like the downforce coefficient, the downforce distribution, the heave stiffness of each of the axles. We have aspects related to the suspension deflection, tire deflection, the stiffness of the tire, which is also variable, and it varies in a very non-linear manner, and it's something that you you need a tire model to have to know how to model that properly. Some results related to roll and lateral load transfers. So what is the roll stiffness of our car at each of the different corners? What is the roll gradient, the roll angle? Some steering results like the Ackermann percentage, the steer ratio, and also the tire results, which, as you would expect, they are the ones that have the largest amount of outputs, including camber angles, slip angles, toe angles, vertical loads, lateral forces, longitudinal forces, self-aligning moments, sliding energies, percentages of usage, and so on. So all of these are just examples of all of the variables that are involved in the mathematical model behind the software. So just to give you a dimension of how complex a car is and can be, and how much knowledge you can get from your car if you model all of this yourself. So again, we focus again back to having a in-house made software, simulation software, and optimization procedure, in which you can learn a lot more than just having a readily available black box where you toss your inputs in, shake it, and see whatever comes out. Okay, so all of that is related to the function portion of our methodology. So all of that was to know what is the best kinematic behavior that we have available to us within our boundary regions. And now we're going to go more into the form. So how we're going to get to those outputs. And pretty much what we're going to do here is that the kinematic behavior that we just found to be the fastest from our skid pad optimization procedure, these curves are going to become inputs into OptimumKinematics optimization module. And these include the toe angle variation versus suspension travel, in other words, the bump steer of the car, the camber angle variation versus the suspension travel, and also front wheel steer angle, the steer ratio versus steering wheel angle curve, and the Ackermann percentage versus steering wheel angle. So this is an example of what happened in the skid pad optimization procedure. So, for example, this is the camber variation that we have versus the steer angle of the front tire. And our optimization algorithm was allowed to search for different curves within the red and the blue curves. And the optimized curve that we found is this green one. So this green curve is what will be input into OptimumKinematics. And we will change our pickup points accordingly to try to get as closely as possible to this behavior. And also in OptimumKinematics, you can also add some more objectives that are not necessarily considered in the mathematical model of the skid pad optimization, including anti-geometries, roll center migration, mechanical trail, upright geometry stuff, and some other variables as well. So for OptimumKinematics, the way that we're going to start is by defining the boundaries of our optimization, just like our skid pad optimization procedure. Every optimization algorithm needs some sort of boundary, some sort of valid input region that it can search within. And in OptimumKinematics' case, that comes in the form of the regions in 3D space where each of the different pickup points can be placed. And these are mainly defined from packaging constraints. So you need to have at least some idea of the final shape of your car to be able to define these, so that your suspension pickup points will not be clashing with, for example, your brake calipers, your brake discs, drive shafts, the gearbox, the engine mounts, the driver legs, and so on. And after that, we will set our kinematic curves as the input into our optimization algorithm. And what OptimumKinematics is going to be doing is that it's going to modify the different pickup points in order to try to get the car's behavior as closely as possible to the kinematic objective that we just found. So this is just an overlay between the suspension layout of the baseline suspension, which is in orange here, and the optimized suspension that the algorithm found to be the best pertaining to our objectives. And we also know how much or how little each of the different pickup points moves in space with the optimization procedure. And here, just to show you, give you an idea of how close or how far we get to our desired behavior that we got from the first software that I showed you. We can see, for example, this is the front toe and rear toe variations in heave. In other words, the bump steer of the car. We see that the baseline suspension, pretty much we had a toe in on the front axle in compression, while the optimization procedure preferred a toe out in compression. And the rear axle had also the opposite behavior from what was ideal. The skid pad optimization preferred a toe in compression on the rear axle, while the original suspension had toe out. And we can see that comparing the blue line, which is the output of OptimumKinematics, and the green line, which is the output of the skid pad optimization, we can see that the two are fairly close to each other. The error that we have in the bottom graphs is relatively low, and it's much closer to what we needed to have than the original suspension. We also have pretty much the same conclusions for the camber variation in steering. We can see that OptimumKinematics is able to get to the target that we got from the skid pad optimization a lot closer than the baseline suspension. And also the same goes for the steer angles of each of the two wheels versus the steering wheel angle, which of course will be a consequence of both the steer ratio and the Ekman percentage as well. So just going over some of the conclusions that we have from this study, from this simulation and optimization methodology that we have developed. We can conclude that this methodology does result in increased vehicle performance. As we saw in the beginning, the lap times of our optimized car is markedly faster than the baseline suspension. And also that OptimumKinematics is able to deliver the different pickup points that will get as closely as possible to those kinematic targets within a small margin of error. And a disclaimer that we need to make here is that these results are specific to this car because there are some baseline characteristics that the optimization algorithm is not touching, is not modifying, because we need to start our optimization process somewhere. So the mass of the car is the same, the weight distribution is the same, the track width is the same. And if you change any of those, the results will definitely be different as well. And another very interesting and important thing in the software is that even if it doesn't cover your car completely, the software does consist of a very good basis that you can start from if you want to tailor the methodology to a specific project. So if you need to optimize different variables, if you need a different mathematical model, for example, if you have one differential, if you have two differentials, if you have a four-wheel electrical motors, if you have a more complex and complete aerodynamic map, the methodology that we have here can very easily be adapted to your specific case. So with that, that will conclude the first part of our webinar today. I hope you learned something from our skid pad optimization procedure that we presented to you here. I hope this is useful. If you have any questions, do send it to us in the chat, that we will answer them at the end. And now Pedro will take over the screen to present the second software that we will be talking about today, which is a four-wheel transient simulation model of lateral load transfer.
Thank you very much, Felipe, for your presentation. It was very useful. I would like to know the feedback, what you guys are thinking about. And at the beginning of the webinar, we read some comments of people asking more time for Q&A section. So here is what we will do. So we will divide the question and answer section in two. So we will have a question and answer section right now after Felipe's presentation. Then we will start the presentation made by Pedro Scatolin with the four-wheel transient load transfer model. And then we'll follow with another question and answer section, all right? So following to our first questions, just a second. Our first question, it's coming from Sanviro. He said that as part of a Formula student or SAE team, I've understood how useful the software is, and if is there any possibility, any chance that our team? I'm sorry. This is the questions that I sent you. Regarding this question, today we unfortunately cannot sponsor Formula student and Formula SAE team because our president Claude, he's a judge in several worldwide competitions around the world, and if we sponsor a team, it could look like that we are having some favoritism, but we have student discount for seminars and for software. So if you go to OptimumG slot student, you can buy our software for a very reduced price. If you have any questions about that, just send an email to us for info@optimumg.com. But following to our question and answer section. Our first question, it's coming from Crystal, and it's asking, how do you manage drift when interpolation measure data?
The way that, let me go back to the interface here. It is right here. So the way that we interpolate all of the different aerodynamics properties that we have on our source or aerodynamic map is it's just pretty much an interpolation procedure which takes into account multiple variables. It's called a quadratic regression that we have here on this title. It's fairly standard. You can see it in a lot of different material, not only related to racing, but a lot of the different aerodynamic models that we have from the aerodynamic map use a similar sort of interpolation. So yeah, I recommend you look into it a little bit further. But just a quick introduction to it is that it gets the points that we have readily available and interpolates this surface to get the minimum error compared to the source data that we have. And the same goes on not only for lift, but also drag and the downforce distribution as well.
Okay, thank you, Felipe. Our second question is coming from Ready to Race. The question is about skid pad optimization tools. You mentioned that there's no transient, but if you have a spring mass roll and pitch inertia in your input data, how do you use it in your skid pad optimization?
Yeah, so on this specific example of the skid pad optimization, this is just these are just metrics that are calculated because we have an idea of how much the roll center moves at every different corner radius. And if you know where your roll center is and you know your roll inertia about the suspended CG of the car, then you know what the actual inertia is about the roll center at every different corner radius. So this is just for calculation purposes in this sense. So it's not something that is modeled in an equation per se. It's just an output that we can calculate from our software, since we have an idea of how the roll center moves throughout the corner.
Felipe, can I make a comment also on this?
Yep, of course.
All right, so you know the story of if you excite a system at its natural frequency and there is no damping, the transmissibility could go banana. So what you always want to make sure is that your pitch frequency or your heave frequency or your roll frequency are not the same. The fact is that on race car with downforce, you want to have a vertical stiffness that is increasing with the speed to have a better control of your ride height. And no matter what, another spring which is in series with the suspension is the tire, and that vertical stiffness of the tire will change with the downforce. And so the natural frequency in pitch, in heave could change, but also in pitch and its roll. So one of the things to make sure is that you can make a graph of frequency in heave, roll, and pitch at different speed and make sure that they do not cross, because you could have problem at that time. So yes, it's not a transient simulation, it's a skid pad optimization. It's always good to have an idea of how much the frequency are changing. And guess what? The frequency are themselves kinematic dependent. That's the notion of the parallel axis theorem. Okay, let's go back. Next question.
Okay, thank you, Claude. Our next question is coming from Owen Frey. He's asking, are there any general guidelines for how corner stiffness changes depending on tire width and diameter? They increase, but how much?
Well, that really depends on the tire models that you have available. So let me go back to the cornering stiffness slide here. This one, yeah. So if you have a tire model available to you, you can very easily calculate that. Without a tire model, it's very difficult to have that information. But if you have the data of a tire test available to you, and you fit a tire model, for example, with a tool like Optimum Tire, then you can have that sort of information.
If I can say a few words there, you have a vertical stiffness, you have a lateral stiffness, and you have a cornering stiffness. When you enlarge the tire width, you increase the lateral stiffness and you increase the cornering stiffness, but not in a linear way. It's not because you increase the tire stiffness width 10% that you increase the lateral and the cornering stiffness in the same percentage. Now, it is true that in very first approximation, the weight distribution of the car and the cornering stiffness distribution should be very, very close in the same ratio. But you can make this theory lie by simply putting 2-degree positive camber on the front and 2-degree negative on the rear, or putting a higher pressure on the front and a lower pressure on the rear. So in first approximation, yes, the tire width should be very close to the weight distribution. And you'll see that on sport cars in the street, not only race car, that very often that's the case. But if you want to have a real good information about that, a very good tool to make a decision, you need to have a tire model.
Okay, thank you, Claude. Our next question is coming from Antonio. He's asking, how on the simulation can you add an error or functioning related to the wear of a component? Is it in the modeling of the function?
Can I answer that question? And Philippe,
sure.
if you want to elaborate,
Okay.
your simulation will be as good as the input. So do you have a timer which take into account the tire degradation, which is very often a thermal tire model? You can you can suppose a degradation and see how much the criteria of performance like grip control, balance, stability, and so on are changing. But the simple and unfortunately the difficult answer to your question is, unless you have a timer which take into account the tire degradation versus the wear and the temperature, you don't know. Philippe, you want to elaborate more on this?
I fully agree with you. It would come from a tire model that has that sort of data available. It's pretty difficult to get that sort of data available, but that would probably be the way, yeah.
Okay, thank you, guys. Our next question, it's a more broadly question. It's coming from Ali Mohammed from Africa. He's asking, could you please talk about landing the first vehicle dynamic simulation role?
I really like this question because one of the things that is coming from the heart in OptimumG work is sharing our knowledge. Unfortunately, we never gave a seminar in Africa. We would love to, but one solution, and Danielle, you will make sure to answer specifically to this gentleman.
Mhm.
We have on our website some link that you can have there with very good documentation and very good video, which will take you by the hand of the very beginning of vehicle dynamic understanding and also simulation, whether it's about understanding the tire, when it's about understanding kinematics, when it's about understanding damper, aerodynamics. So, Google it and type OptimumG or type Claude Rouel. There are many videos that I made, some of them like 15 years ago, but they are still very up to the point. So I would start with that, and then if you have specific question, you can always send us an information there. Yeah, a question. Sorry.
Yeah, of course. We would love to help with that. The next question is coming from Car. Do you recommend creating your own quasi-steady bike model before creating a transient bike model?
Yes, absolutely. For two reasons. First, because we need to start with the simple stuff, and it's a lot easier to do a steady state system than a transient system, simply because in steady state you don't need to necessarily work with differential equations. You don't have a time step involved. You don't have the previous state of the car influencing the next state of the car, because everything is constant. So always focusing on the simple first is a good approach to having an optimized design methodology, an optimized approach to simulation procedures. And also the second reason is that even while having only a steady state bicycle model, you can still learn a lot of information from it, especially if you're a Formula student team that is just starting. So yes, I will absolutely recommend to you that you should always focus on simpler models first before you try and improve them and get them more and more close to reality.
And I want to insist on that. Simple, then complicated, not the other way around. If you cannot take a good picture, I don't think you can have a good movie. If your car is not good in steady state on a skid pad or right at the apex of a corner, which is a steady state for just a few hundred of a second, if your car is not good in steady state, don't hope to have a patch on the patch to make it better in transient. Simple, then complicate. One wheel, two wheel, four wheel. Increase the degree of freedom, go from steady state to quasi-steady state to transient. And of course, this, I insist, show you what the beginner guys, the beginners at OptimumG are doing. And we have models which are more sophisticated that either we sell or we use our in consulting operation, or that will go one of these days public. But simple, then complicate. And for the guys who want to write their own software, I can use the opportunity, write your equation on paper before you write one line of code. Write all your vehicle dynamic equation before you even write one line of code. Do we have another question, Danielle?
Yes, we have a last question. I believe it's just a review about what we spoke yesterday. It's from Francesco. He's asking, what is the difference between steady state and quasi-steady state?
Yeah, so this is something that we went into a little bit more detail yesterday. So the recording from yesterday is available on our YouTube channel. You can check it out. But answering your question, in steady state, what you have is pretty much that you have a situation where the behavior of your car does never change in time. So your slip angles are the same, your lateral forces are the same, your lateral acceleration is the same, your ride height is the same, and so on. A skid pad is necessarily a steady state simulation, or a steady state condition rather. And to have a steady state condition, you necessarily need to have a yaw moment equal to 0 and longitudinal acceleration equal to 0, because if you don't, then you will vary either your slip angles, which will vary your lateral acceleration and your lateral forces and so on, or you will vary your speed, and you're no longer taking the same exact radius forever. Quasi-steady state, on the other hand, is a simplification of a transient state, where pretty much you are analyzing a transient situation as a series of steady state instants in time. So to do that, you need to assume that your variables vary slowly enough so that you can apply the same equilibrium conditions that you would apply on your full steady state model. But on the other hand, you don't necessarily need a yaw moment equal to 0 or a longitudinal acceleration equal to 0, because you're only analyzing one single instant in time in complete isolation from what happens before or after that.
Okay.
All right. Before we go to Pedro's work, Luca, you are a big part of this two-wheel model Transient that we explained yesterday, and you also work very hard, especially for the kinematic optimization. From your point of view, if you had an advice to give to the beginner of people who work in vehicle dynamic simulation optimization, what would it be?
Well, I think it's pretty much what we have spoken today and yesterday as well, but always follow the road that you need to start. Simple, then complicated, and for vehicle development, we always need to follow the form, and we need to follow the function, then we go to the form. And that's a mistake that happens quite often, is that normally your formula student team or you as a designer just need to build a vehicle, and then you just Google in the Google images for suspension or whatever you want to design, and then you just copy the thing. So what I suggest to you is to first you need to think about what do you want to do, and then you need to build the foundations and so on. So for example, if you want to build a suspension, you first need to look how your tire is going to behave. Or for example, if you want to do a vehicle model, as Claude said quite before in some minutes ago, draw your own free body diagrams, put all the forces, moments, all the distances there, all the velocities in a paper, and then you start to write all your equations in the paper as well, either if you are going to do intransients in quite steady state, but always follow the rule that you need to start first simple, then complicated, and you need to first think about the function, not the form. So that's what I think would be a good advice.
And I would add one more thing. Students especially are literally obsessed with lap time simulation. And don't get me wrong, it's the most important thing. Lap time is the only number that doesn't lie. But here's the reality. Simple then complicated. By doing a simple ISO test and having performance criteria like lateral acceleration response time, or yaw velocity damping, first with a two-wheel, then a four-wheel model, then recreating that on the track, you will learn much, 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 much more than with a lap time simulation. Lap time simulation is the ultimate goal, but it should be the last thing you should worry about. You want to learn the car. Otherwise, people are using simulation as a black box. You change the entry bar. Oh, the car is quicker. Yeah, but can you explain why? No. So a good way to practice simulation is to start with a simple simulation like ISO test, and ideally repeating them, because as I keep saying, all simulations are wrong. Some are useful. The useful one are the one you trust, and you trust them because, ta-da, they have been validated. Okay.
Just because you mentioned it, Claude, you were talking about people obsessed with lap time simulation. So yeah, I spoke about simple then complicated, function then the form, but why? I forgot to mention that. It's because you need to fully understand what's happening with your vehicle model or with your vehicle or with your tire. So that's why we need to start simple and complicated. Otherwise, we are just, like Claude just said, you are going to put all the inputs in a box, shake that, and see the results. So that's why we at OptimumG, we prefer to do this. So every single engineer, every single software developer, every single intern are going to understand fully on what's happening there with your vehicle.
Good. Okay.
Okay,
Daniel?
thank you. Yes, thank you, Claude. Thank you, Felipe and Luca, for your contributions. These were our first Q&A section. Remember that we will have another Q&A section after Pedro's presentation. But before we dive deep into that, Claude, would you like to say a few words before we start with Pedro's
Yes.
presentation?
Pedro is going to present you a simple simulation, which is in C++. It's an open loop, I insist. We invent a lateral acceleration or a steering input. It's an open loop transient load transfer simulation. Pedro contacted me a few months ago saying, I want to be an intern at OptimumG. I said, okay, so let's give you a little challenge there and let me know, show us what you are doing. And the beginning was a little bit difficult, but I gave him a lot of support. We spent a lot of time together. And then he ended up doing a pretty good job. And I think what Pedro is going to show you is a very good example of what students should do in a simulation. So Pedro, that's going to be your show now.
Hi guys, so I'm Pedro. I'm the newest here in the OptimumG team. I'm an intern at the engineering team. So I will show to you guys the software. So the software.
We lost.
Hi, everybody. We're just facing a technical issue here with Pedro, but he should be back soon. We apologize for that, and we are already working for solving this. Meanwhile, we would like to know what you think about Felipe's presentation. If you have any more questions, what do you think was the most impressive or most important thing that you have learned? Okay, Pedro is back.
Uh-oh. Pedro, are you online? During the time we try to make Pedro's connection working, I want to insist on one thing. When we hire intern, is with the firm ID that they will come full-time working for OptimumG. That's why our selection is kind of demanding. But Pedro very much succeeded in there, as well as before Felipe and before that Luca. Pedro, are you able to connect with? Oh, yeah. Okay, we can hear you.
I think we unfortunately lost him again. Guys, we already apologize for that. We are solving this with Pedro. We're finding some questions that we received yesterday, and we will try to answer meanwhile. If you have any other questions, please feel free to send in the chat, and we will do our best to answer them. I think Pedro is coming back.
In the very worst situation, Felipe, do you think you would be able to work with the software there of make the presentation? Pedro, yeah?
Hi guys, I think now it's all right. I don't know what happened.
Okay, let's try.
Okay, so I think you guys can see my screen right now.
Meanwhile, it's time for everybody to have a cup of water.
Okay, now it's all right. Sorry guys for that. I don't know what happened here, but this software, it's an open loop software, and it's it's not a simple software. And you guys that are from like Formula student teams, some of you, I know that you guys don't have a tire model, and you guys will see like how a lot of informations and optimizations you guys can have from a software that doesn't need the tires. So in the beginning here we have this tab that's about all the inputs. So we have the mass inertia inputs and all the dimensions ones. And here we have the suspension inputs and the steering that we're going to talk about, the tire width later on, the dampers, and the tires, that's the vertical stiffness and the damping of the tire. Here in the dampers, it's good to say that here we have a simplification. The dampers are linear, and they are the same in rebound and compression. So we have a lot of types of simulation right here. The first one, it's a single simulation. That's a simulation in the time, and we can enable the steering or not. We have batch runs. We have one batch runs. We have a batch runs with 2 parameters right here, and a batch run with 4 parameters. This guy, we're not gonna talk about it because you're gonna see this next page right here. That's the parallel graphs. That's very near what we're gonna see here. And this tab, that's something that we're trying to. It's in development, and I'm gonna just show you here the results. But in the theory, it's to have what what you want to optimize. So it's like a transient score ranking. Here I have the setups, and then you could compare the original car with the new car about the roll angle response and in your lateral acceleration. So come back here. We're going to start doing some simulations. So the first simulation will be half sine profile input of lateral acceleration, and we're going to run it, and we're going to see in the analysis part about our plot. So we can have a lot of variables to plot right here. So in the input ones, we have the acceleration. That's what we did. And then we have like the roll angle of the car. We have the roll rate of the car, and then the roll acceleration. You guys can see that if I can insert all 3 here, we have different operations in each one. So these will be very important to you to us to analyze later about the load transfers and when the load transfers happen. So coming here in the load transfer, we can open the components tab and see about the geometric load transfer, the spring load transfer, the anti-roll bars load transfer, dampers, and then the unsprung mass load transfer. So first of all, let's see about the contribution. We can see here that in the first beginning of the movement, the geometric load transfer are most part of the contribution. We can also see that the dampers have a really big influence right here, and the unsprung mass. In another way, in the middle of the movement, we can have the springs contribution, and then anti-roll bars contribution. Our anti-roll bars contribution here. So another thing that we can analyze in these graphs is about our force and how we can have it. Let me just plot right now. So if we get a zoom right here, we can see how lazy our car is. So we can analyze that the geometric load transfer happens in the extent of the input. We can see that the anti-roll bars and the spring ones happens. Let me plot the spring here. The spring ones happens later. And then we can see that our dampers, that's in orange, and our unsprung mass happen first. So this is something that that you guys can see, like in some way your car don't behaves well in the beginning of the curves or turns, etc. And then you can analyze here if it's coming from the spring load transfer, it's from the anti-roll bars, it's from your damper, where is from that difference. Besides that, we can have some analysis and our frequency domain. So we're gonna get here and do some simulation in a chirp uh, profile, and then simulate it. And you're gonna see here in analysis the frequency domain, and we can insert like our let me see, row angle, and then we can see our response about the frequency, or we can see like about our wheel loads and see that would be probably our natural frequency of that case, that peak right here. We can also see the phase diagram and this currents graph. That's something that Claude could possibly speak later on. Also, we can go to veterans. So here in veterans, we can do a simulation with our geometry, and we can change our front row center, our rear row center height. Let me just come back to the half sign profile, and then we go to run the simulation. The simulation is starting, and it will run, and we're gonna see about how our row center changes with some other parameters. So when we come here in the batch 1D, we can have this one that's our extremes, and see like how our row center, the movement, the height of row center changes our lateral load distribution. So we can see this curve that if you have a higher rear row center, you get less load transfer distribution right here. And we can see all these channels. Going back to simulation, we can do two batch parameters here, and I will do something really nice. First of all, let's go back to plots right here, and we're gonna see about our steering. Let's come to the time domain, and I will simulate our car with a tire that's not just a point, but it has a width. So it will be 100 tire width of 100 millimeters. And then we come back here in simulation. We enable the steering. We're gonna get 200 degrees of steering in our steering wheel. And we'll come here and put a linear profile, and we will just have our steering. So no lateral acceleration, no delay, and just steering. We're gonna run the simulation, and then come back here in analysis, and we're gonna see about the load transfer. So here we can analyze how the load transfers in each wheels will change with just the steering. So if you have your car steady, and in your setup base, you can see that how much your wheels, the front left tire, the front right tire, will change this in the scales. And that's very important, because when you're making a turn, you will have also this change in your loads, and you need to know by how much to quantify the difference or something clear near to it. Something that's very nice to see, it's about our the right height of the car. So without the tires treads, we can see that the car really doesn't change so much. But when we have a tire that we have some width in the tire, we can see that our car lifts up by 1.2 millimeters, or something like that. And it's very important too, because you're making like a turn and you have your aero package, and this is changing about what would be your location in your aero package, balance, etc. So we're gonna do now 2D bets. So we're gonna back here with a profile of 1G. All right, and let's put some delay to the start and change the duration here back for our, and we're gonna continue with this steering one. So let's do different. Let's do just the steering. I think will be better. So here we're gonna change our steering angle, so would be 20 degrees in the wheel, and we are changing our tire width, so it's going to be to 0 to 500. All right, and we're gonna run. So you're running now the 2D batch, and you're gonna analyze by how much that the tire tread changes our lifts in our car. So I don't know, guys, if you are like seeing some little square here in my screen, because I think that was the problem. But yeah, so it run. Let's come here, and now we can have a lot of visualizations here. We can have a 3D visualization or a heat map visualization. In my opinion, that's the better one. So we're gonna search about the channels right here, and we're gonna plot our steering gain with our ride height. So as you can see here, like just me try to insert in 3D, we have the tire tread in this axis, the wheel angle in this axis, and by how much our ride height changed in the front axle. If I insert right here the rear one, we can see, but it's so less. All right, but let's see about the front. So in contour graph, we can see that when we're when the wheel is 0, it's not changing so much. But here in the extremes, you can see that the car is lifting up about 7 millimeters. That's a lot of to what we have without our tire tread. So we have some other things to see right here, and we can make a lot of analysis with this batch. We can run like your springs changes in the front and the rear, and see by how much your roll angle are changing. All right, you can see everything you want. Something cool that we can see also here in the batch runs in the 1D is something that I call like a dynamic one. So you can like click play and see how that curve is changing. Let's see about our roll angle right here. So here's our roll angle in the car. You can click play and see how it's changing by the time. So when the profile of that acceleration it's running. Now let's go to our parallel graph parts. You guys already see that this kind of graph in the other presentations. It's a graph that's very useful for all the things that you want to understand, because you can like if we go back here in 2D batches, you guys can understand that we can just like analyze 3D dimensions. So how we can analyze 4D dimensions? If we have to simulate something with 4 parameters, how are we gonna see it? And with 5, 6, 7 parameters, how we're gonna analyze it and know about how it's changing and by how much. So parallel graph, it's a useful tool for it. In this case, we have a lot of inputs here in blue ones, constraints here in the orange color, and then black ones here for our outputs that would be LLTD, that our lateral load transfer distribution from the front and rear axle, and our damping ratio in row. So if we have all these combinations of parameters, we would have this row gradient and these parameters. If we change the front track for a higher front track, we will change the outputs. If we lower our row center in the front, we're gonna change also the parameters. Also in the rear, if you're gonna get down the row center or up. So, okay, now it's something useful. We can change like the spring right here and the motion ratio, and we can see by how much our lateral load are changing. But let's do optimization for it. So it's a internal tool inside of this graph that I created. Claude helped me a lot of it. He gave me the idea, and I tried uh, to build that. So let's say that we have a car that's not so well that you want to be, and you want to change not only one thing but a lot of things, but also you cannot change your front track. So we're gonna lock this parameter. The rear track, we're gonna lock this parameter, and the rear row center. All the other things you can change. uh, so we locked these parameters, and then you want that your row gradient has a target. So you insert a target in your row gradient that gonna be I don't know, 0.48 degrees per G, and you want to find a LLTD distribution. So when we click like here, we can also change that target. So we can have LLTD about, I don't know, 50% here, and this parameter that we locked are not changing, just the others. But we also want to have a damping ratio. That's not this one. So we're gonna change the target of that damping ratio, and then we're gonna change all the parameters. Let's say that we're not gonna change more our rear motion ratio. So we're gonna lock this one, and we can, I don't know, unlock the row center and create the new targets for the new parameters that we need. It's a useful tool. You can like insert a lot of inputs. All that inputs that are in the first page here in vehicle, you can change about it and generate this graph with a lot of information. You can pass like we can do one day just changing these parameters and seeing what's happening. And the next page would be the 3D parallel graphs. So here in the 3D one, we have something that's very nice. We have that's the same graph of the parallel one, but think guys, here we have something that is static. We don't have things that are changing with your lateral G's, and we have a model that can do that. So why we don't change the simulations? So the 3D parallel is the same of one. We have the dimensions. So the 2D would be this one. We have the dimensions about it, and we have the values and about that curve. So, but if we insert like the lateral G here, and we create some parameter that's varies with our lateral acceleration. So let's create some case right now. Let's say that we're gonna optimize your spring motion ratios, arbs, and arb motion ratios. So we have a lot of curves in that case that you guys can see. When I click the curve, it's on the side right here. Let me get this. Say that we're gonna get a LLTD target. You do not want a LLTD that's constant, but that varies with the lateral acceleration. Something that we can like take as example, the Felipe talked to us and saw and he showed us that in the optimization, in the skid pad optimization, the LLTD would vary with the row angle. All right. So in that case, or in the row, the turn radius. In that case, we can transform that in our lateral acceleration and generate some curve about our LLTD curves. So it's let's, I don't know, put some values here. 2 on A, B will be -3, and C will be 50. So we generate this curve. So in this region, we're gonna have a lower lower LLTD, but in higher accelerations we have a higher LLTD. Also, you do not want your car to have a roll gradient that's constant. Let's say that you want your car when it's with more load to be more stiff. So we're gonna create here something like that. Let me see, 0.3. So your car will gonna to 0.33 degrees per G to 0.5 degrees per G, or in this case, it's not going to be stiffer, but it's going to be less stiffer. But all right, that's not the case. So here we have the two curves and all the parameters in the middle. When you click in the run, the optimization will run all the points to trying to find these curves. And with these curves, we will have a lot of variables that will give us some return curves. So that's something that Claude said, that that's abstracted approach, because with that curves, we can insert in OptimumKinematics and have the kinematics points. So let's say about our motion ratio in that case. So that would be the curve about our motion ratio. Let's say with our anti-roll bar motion ratio. In that case, it optimized to these values. Let's say about our spring rates, about our I don't know, anti-roll bar stiffness. In that case, we can have these curves and later on analyze and make better simulation, better optimizations with them. And just to show something, let's say that you don't have a spring rate that cannot be constant. So you can do something here. Let's say that this would be our new spring. You lock these parameters. Let's say this one also. So will be 14 here, 14, and also 0 in the other ones. And we're gonna lock all the our springs. And we click run again in the simulation, and our program will try to find new curves for other parameters with a spring that's constant. We can do also with the motion ratio curves or the anti-roll bar curves, something like that. So we have the targets that we achieved, but now with our values, so our spring values that are constants. What so this is it's a very useful tool. Here we can see about the dimensions and how it changed in each way. So we can see that the springs are just a point right here, but the motion ratio will be a curve. The also our anti-roll bar in the rear will be almost constant in that case, and that it's very ways to analyze by how much that parameters are changing in your in your lateral movement, in your lateral acceleration. Sorry. So also we can, let me see here. We can do another 2 batch parameters. Let's say that we're gonna change our geometry, our front CG, our front row center height, and also our rear roll center height and see by how much we have some difference. I need to change here about our inputs. Let's say this one and this one. All right. And we can also run. So we can now see about how our car are changing with different geometries of roll centers, or you're trying to do some design approach to know by how much you need to change, or that output will be more or less sensitivity to rear or front roll center height. So we can see about, like, I don't know, our, let's see, our geometric load transfer. We can see right here about the difference with the front and rear ride height about our load transfer. That's almost a linear pattern right here. We can see with our roll angle. We can see about the roll acceleration, the loads in each tires, and I don't know, the camber, and the positions about the unsprung masses, the natural frequencies, the damping ratios, etc. So that's something that you can analyze, and it's a simulation that we can have for a lot of parameters. So I don't know, maybe Claude, you want to add something to our demonstration right now?
No, well, yes and no. No, because we are running out of time and we still want to use a little bit of time for question. And I saw many interesting questions coming from. There is one thing that I want to insist, and I think you do it very well on your software, Pedro. You can make a 2D graph, you can make a 3D graph, you can make a 4D graph with color and 5D with patterns, and then boom. How do you make a 6, 8, 9, 20 graph? And that's the parallel coordinate presentation is so useful, and especially it's a kind of optimization. You lock all the parameters, but let's say you front and rear interval bar, and you say, okay, I want to have that roll stiffness and that lateral load transfer distribution. Give me the front and the rear interval bar stiffness or motion ratio that I want. And then on top of that, you can do it in 3D. In other words, I want to give a given lateral load transfer and a given roll stiffness that is not linear, and it is changing with, for example, the roll angle or the lateral acceleration. That is very, very good, and I think the people should work on this. It is bloody useful. It's very, very useful, and I think you should do that before you go to neural network and things like that. Again, AI. Neural network, machine learning, super useful if you know what you are doing. Otherwise, it's going to be, you're going to try tons and tons of solution. It's going to give you an answer, but you won't understand why. And the day you are asked, why is it getting this result, and you cannot answer, you could be in a trap, put yourself in a trap there. Danielle, I think we need to switch to questions.
Yes, sure. Before we switch to the last Q&A section, we have a very nice thing to mention. It's coming from, just a second. It's coming from Quadra. I'm sorry if I'm not pronouncing the name right. He said that he just got a new job regarding chassis and suspension roll in an OEM. Of course, there's a lot of merit of him, but he mentioned one of our seminars. So we are very happy to have this feedback, and we are happy to help you with this new professional state in your life.
So this guy
So
said
our-
he had a job because of the seminar he went to.
yes, correct.
Well, there are many examples of that. Many.
Yes,
Yeah.
that's very, very nice. We love to hear your feedbacks, guys. If any of you have already attended one of our seminars, the AVD or the data driven, we love to hear. If you want to write for us, we would love to read and to publish and share with everybody. Thank you for sharing this with us. But going to our first question, it's coming from Ready to Race. It's still regarding the software presented by Felipe. He's asking if you use any tire temperature models.
So on that skid bed optimization example, we are not taking into account any tire temperature or wear effect because that would require some elaborate models. And of course, the software can be modified to take that into account, but at this point, the results I showed you today do not take that into account.
Yeah, but Felipe, you calculate the energy lateral and longitudinal going in the tire, which is
Correct.
already an indication of how the tire is going to store energy and change its temperature.
Yes, that is a metric that we can calculate in the software. The energy that goes into the tire, the sliding energy, is simply, well, the sliding power is simply the product between the force and the sliding velocity. So the lateral force and the lateral sliding velocity, or the longitudinal force and the longitudinal sliding velocity. And the energy that goes into the tire is simply the integral of that versus time. We can calculate that in the skid bed optimization, yes.
Okay, thank you, Felipe and Claude. Our second question is coming from Facecar. He's asking, how do you validate the moment diagrams if beta is difficult to measure?
Okay, I need to answer that question two ways. Number one, you would be very surprised that you can measure the slip angle at a really low price. I encourage you to look at or contact the people from Sensoric Solution in Germany. They are helping a lot of Formula student team with their slip angle sensor at a very moderate price. So up to you. That being said, I need to insist on that thing. You don't know what the beta is, but you know that if the beta is that and the steering angle is this, that's what's the yaw moment, and that's the lateral acceleration are going to be. All right. You never know exactly what your driver or your test driver is going to complain about. But you have all this you have a box with all the simulation being produced before even you go on the track. So once the driver tell you, I have an understeer in turn one, I have a braking stability problem at the entry of turn 7. Well, for that kind of speed, for that kind of tire, for that kind of track temperatures and so on, then you know what's the solution. Because you give a car with a specific understeer problem, you take, I don't know, a Ferrari GT3, and you give it to 5 engineers, and I bet you that I wouldn't be surprised that 5 engineers will solve the understeer different way, with the camber, with the tire pressure, with the ride height, with the spring, with the damper, with the entry bar. There are many ways to go for it. But there is only one which will give you the best understeer, the solving of the understeer, the best balance and lap time consistency for that driver on that track, in this track and atmospheric condition, and for that tire. So you never know exactly what's going to happen, but you need to have a toolbox ahead of time to calculate all your simulation. And that's what we do. So we don't know what the car is going to do. You change the track temperature 5 degrees, it's a different condition, but you are ready to work on it. I think we need to go to the next question.
Yes, our next question is regarding to books and literature. Actually, we have 2 questions related to that. I will unify in one. The first is from Carrot, is asking, what books do you recommend to complement the basic concepts that are used? For example, derivatives, physical concepts, etc. And Francesco is asking, is Performance Vehicle Dynamics by Bike Wheel is a good book for vehicle dynamics? Before we go into that, I would like to say that we will send you an email with some books recommendations after this webinar. But if you would like to complement on that, Claude?
Well, again, I mentioned that yesterday. If there is one book I would work with, is The Science of Vehicle Dynamics from Massimo Gugliani for the vehicle dynamic part. For the programming and the mathematical, I am not the best person to answer that question. Maybe Felipe, you have an idea?
I have some ideas for
Yeah,
the concepts in engineering, mechanical engineering especially. For calculus, I would recommend the James Stewart book. For physics, I think the first volume of Halliday may be enough, so you can have an idea. For dynamics, I would suggest the Hibbeler book. And for numerical methods like Hunchkuta, OD45, you can have a look at the Chapra book. It could be useful for you. For programming, I think maybe Felipe is better to talk about that, but I can suggest Clean Code just so you can have a general idea of coding and some guidelines as well.
Yeah, I agree with the suggestions. Most of these books are familiar to all of us here at OptimumG, and we would recommend them. Yeah.
Yeah. Thank you, guys.
What I would suggest is that in the YouTube, as a comment, we give this book ourselves. We put that book ourselves. Recommendation.
Okay. And we'll send an email with some recommendations as well. So our next question is from Pablo Rodriguez. In a parameter optimization process, in which cases do you consider introducing machine learning would be profitable?
The answer is, for me, not until you demonstrate you fully understand and can use the basics of vehicle dynamics. That's a simple question, a simple answer.
Yeah, of course. The next question is from João Esteves. What are the most important parameters to monitor from the car sensors, and which sensor are the most important?
Well, it depends for what. I mean, that would be the object of a webinar of 2 hours in itself. What's your budget, what's your experience, what's your knowledge of vehicle dynamic, and so on. In the data-driven performance engineering, we spend a lot of time about describing the different sensors that you can use, what is their usefulness, meaningfulness, budget consideration you have to take. So it's a very good question, but we cannot answer that question in 2 minutes.
Yeah. Thank you, Claude. Our next question is how we can find optimum camber and camber gain by skid pad optimization.
Well, the skid pad optimization software that we showed you earlier, one of the things that it's trying to achieve is to find what is the optimal camber for every different turn radii that we're evaluating for that car. And one of the ways that it's trying to do that is by modifying the camber gain curves versus heave roll and steer wheel angle in the case of the front axle. So the optimization algorithm that we have developed, one of the things that it's trying to optimize is exactly the camber gain. Yeah.
Thank you, Felipe. Yeah, go ahead, Claude, if you want to say something.
No, that's it.
No? Okay. Our next question is coming from Alain. Why the unsprung mass load transfer is so slow?
It's a very simple answer. It's called inertia. That's all. It takes more time for the sprung and unsprung mass to wake up for a lateral acceleration. And if you agree that it is at the beginning of the corner that you make the difference, then you realize that at the entry of the corner, it's the geometric load transfer, which is kinematic dependent, and your dampers, which are making the biggest difference.
Yeah, thank you. The next question is for Pedro. Antonio is asking if you code your software on C++, and together with that, we also received a good feedback from reading, saying that the C++ simulations are always beautiful to see. If you want to elaborate on that, Pedro, and of course, Claude as well.
Yeah, so the simulation of the software is made in C++. It was one of the requirements that Claude said to me to do, because but it's really, you cannot do like a really good software that's it's fast in another language that's not C++. It's not only C++, it has the graphical interface that's not C++. In that case, it's Qt, and also have a little of Python to do some connections with the Qt and C++, some exports, something like that. I'm a mechanical engineer, so I'm not familiar with all the languages. And yes, I think that would be something way better to do, but the main core of the simulation, the vehicle simulation, needs to be in C++, and it's very good to do it.
Yeah, thank you, Pedro. The next question, also from Ready to Race, is asking how many hours did you spend on these tools?
Yeah,
on average, of course.
Yeah, so for coding the vehicle itself, it's I don't remember, but it was like something like a month to do. But with Claude, we always made some meetings, team meetings, and we always have something to add to the model. So in that case, the inertias, we're gonna add the roll centers are moving, are not constants, the tire treads. So always that you insert a new parameters in your model, you use more time, and also to make all the visualizations, the graphs, and how you're gonna see that, you're gonna utilize a lot of more time. So I think in it's a ratio, you're gonna spend 30% in your vehicle simulation, and 70% if it's a software that's well developed, in creating ways to see about that data. So yeah, about hours, I don't know, maybe probably 4 months, 5 months of work that we did this work, and I'm still improving some other things. So yeah, I cannot say like how much hours, but I can say that ratio. You're gonna spend a lot of more time doing the analysis than the model itself.
Yes, thank you, Pedro. Our next question, it's a general question for OptimumG, Claude, if you'd like to answer. Ready to Race is asking, when you work with your customers doing any analysis of their cases, what is the proportion between steady state versus transient analysis?
Well, that's not really a proportion, and the difference, the delta or the proportion of time we spend in steady state and in transient depend from one customer to a team. The first thing is that, do they have the input that you can trust and that can be validated either by on-track testing or laboratory testing? So there is no answer because of the percentage of time we spend with steady state and with transient, because it depends from one customer to another. One thing is sure is that we always start with steady state. If you cannot have a good car in steady state, you're going to have to use patches on patches, and you are not going to get the best result of your car. Make a good car in steady state, then make a better car in transient, not the other way around.
Thank you, Claude. Our next question is from Denis Slovak. He's asking how changing the track width on one end to the car affects load transfer and load transfer distribution, and how do you define the tire tread with it?
Well, this is a topic which is outside the presentation here. Come to one of the OptimumG seminar, especially the Applied Vehicle Dynamics seminar, and we will elaborate on that. Just understanding the load transfer. There are some video that we have posted. There is a first part which is already posted on load transfer. There's a second one coming soon, explaining suspend, non-suspended, and then geometric and elastic load transfer and the effect it has on steady state and then transient. But this is outside the scope of this webinar. And even if I wanted, I cannot explain that in just a few minutes.
Yes, our most recent video on our YouTube channel is about load transfer. So we suggest you to watch it, and of course, watch it as well, our older videos. It's very, very useful. Our last question for this Q&A section is coming from FaceTcar. He's asking about validating the simulation. So what does validating your simulation look like? It is overlaying your telemetry data to match as closely as possible. What other strategies should be used?
Well, it never, well, it never perfectly, let's say it this way. As I said, let's say you do a simulation. Let's say you use a lap time simulation, which, as I said, is the best, the latest thing that you should do. And your simulation is perfect because it's validated by data. Okay. And it's exactly the same lap time, the same profile versus time or distance of the lateral acceleration of the steering, of the damper movement, and so on. Good. Then you put Max Verstappen driving your car, and he explode the lap record by 2 seconds, and your simulation is not good anymore. So you work in delta. You never work in absolute value. But to answer your question, the question is that, are you perfect? The question is, how can you improve to be closer and closer to the reality? It's okay if the data do not validate the simulation 100%, providing that you understand why and you can refine the loop better. But if you want a specific answer to your question, the answer is this. Yes, at OptimumG, we ended up having simulation software and data which were very close to each other. We can tell you, for example, that at Aragon, at the end of the straight, at 282 kilometers an hour, the front right guard will be 13.5 millimeter, and the damper will have that length. And if we are wrong by 0.5 millimeter. It's that close we are from the reality. But the reason for that is not that we have good simulation of treat and of data. It's first because we have good input, and because we have good tire model, because we do the tire testing ourselves and create the model ourselves. Because we do KNC testing, because we do CG and inertia, because we do damper testing, because we do 7-post rig, because we do wind tunnel aerodynamic map. First thing is to have good input before you even could have a good simulation. But it's mainly because of the input, more than the simulation itself, that we ended up having test data very close to what we predicted with the simulation.
Yeah, thank you very much, Claude. We are approaching the end of our Q&A section. I would like to thank you, Claude, Felipe, Luca, and Pedro, for answering all these very good questions. And thank you guys for asking and attending this seminar. And before we finish this event, this seminar, I think the guys, Felipe, Luca, and Pedro, would like to say a few words. So take your time, guys.
Yeah, well, I think I'd like to thank everyone for joining. Thank you for all of your questions. They are just as good for you as they are to us, because we also learn a lot by understanding what you guys don't know, and explaining the concepts is always a second opportunity to learn as well. So thank you very much for being here, and we hope that you get some knowledge out of this, that this has been in some way useful to you, to your engineering career, to your racing career, and that you can apply something that you learned from us.
Yeah, and I would also like to complement what Philip said. And for I would just like to say some words about the support that we get at OptimumG while developing our tools. So as I think Pedro mentioned it before, so sometimes during the development, we end up having a lot of meetings with Claude, spending several hours just thinking about and brainstorming on how to improve our tools. Also, we chat a lot in WhatsApp or whatever Teams, and we always discuss about we always discuss about how to improve the tools, not only Claude, but we also talk with the entire team at OptimumG. So we always talk about this with the software developers as well. With the software developers, the main reason we talk with them is probably about the code structure and how to code the software, how to organize everything. So that's a little bit of our work. Most of the time we spend just brainstorming and think about how to improve the things than just coding and analyzing the results. So that's it pretty much. I would like to talk.
Pedro, I'm going to ask you, before you were even an intern and you tried to make a demonstration of your skills to be accepted as an intern, how many lines of WhatsApp message did we have together? How many hours of team meeting did we have?
Yeah, I think I don't know. Claude was on my top 3 messages. So yeah, I talk a lot with Claude, and appreciate the opportunity to show to you guys the software, and has a lot of things to improve. Claude was essential in the software. I can say that, like, in the beginning I said, okay, that would be easy, and I will make the model, etc. Are in the books, the model. But then when Claude we start talking in the meetings, we see I saw that have a lot of problems and situations that are not trivials, that you cannot know earlier. And then Claude came with all that experience to help us, not only in the internship test, but right now with the software that we are developing. And it's always a pleasure to work with all these guys. I'm the newest here, and also I'm sorry about the technical problems we have. I don't know what happened with my computer, but everything went fine. So yeah, thank you guys.
I would say this, and it's probably going to be one of the last thing I will say during this webinar. The motto at OptimumG is knowledge shared is knowledge squared. You have many consulting in vehicle dynamic consulting firms. They do a very good job. We are certainly not going to try to compare or diminish their value. But the difference between them, and us is that most of the time, this consulting firm will solve the problem with you. They will tell you that's the kinematic you need, that's the engine that you need, that's the one. But when you ask them, how did you calculate them? Boom, suddenly because for them, knowledge is power. And we have adopted a different attitude, a different business model. We not only deliver performance, but deliver the knowledge that's go with it. And yes, the risk is that after 2 or 3 years, people will tell us, okay, we can fly on our own, we don't need you. But that could be quite there is a risk that after 2 or 3 years, the customer will say, okay, we don't need you anymore. We learn everything you need. But guess what? 90% of the time, the people said, hey, we have another challenge which is a little bit bigger. Are you interested to work with us? Knowledge shared is knowledge shared. And that's what we do in our seminar and as well as in our consulting activities.
Yes, thank you very much, Felipe, Luca, and Pedro, for sharing your words, and of course, Claude. Before we finish this webinar, I would like to ask you, Claude, if you would like to say something else before we finish.
No, first of all, it was being pretty long. We exceeded the 2 hours that we gave ourselves. That's probably because we had a lot of very good questions, and we couldn't answer all of them, by the way. But I think that, you know what? I'm going to tell you something which has nothing to do with vehicle dynamic or with this webinar. Do you passion your job, not the other way around. 95% people in this world, they do a job. When you ask them, is this the job you were dreaming of when you were a little boy, a little girl? Probably not. Because you have an education, which is the case of probably the majority of people who follow this webinar, because you have the parents who allowed you to go to university and learn, you can have your job which is fulfilling your passion. Don't make your passion your job. Don't make a job which is fulfilling your passion. That's what I want to do. And this is what we have at OptimumG. The guys are working a lot of hours. That's not necessary. I don't ask them to work so hard. Sometimes I have to tell them to lift up. But they are learning because it's their passion. And that's what you want from life. You want to make a difference, and you want to understand, to get better result, and understanding why. If you don't understand why you win, you will not understand why you lose. If you don't know your strength, you don't know your weaknesses. That's probably the last of the things that we will tell during this long webinar. And I want to thank everybody at OptimumG and our followers.
Thank you very much, Claude, for these amazing words. We would like to thank you in name of all OptimumG, your presence in this webinar. We would like to know if you would like us to do more webinars, which themes, which topics would you like us to cover? And thank you very much for attending, for sending questions, and for trusting in our work. We hope to see you soon in Formula Student events, in motorsport events, or in other opportunities in life. And thank you very much for attending and for trusting in OptimumG.
Thank you, guys. Bye-bye.
Thank you.